Welcome. In this video, we are going to talk about percent ionization and how we might apply that concept to various acid-base scenarios. So first, let's remind ourselves of the idea of what it means to ionize. So when something is an acid or it is a base, like when I stick an acid in water, what it does is it splits apart into these ions, right? This is the process of ionizing. We have a neutral molecule that is forming ions. So when we talk about percent ionization, we're seeing how much of this original reactant is going to ionize and turn into products. So does 5% of it ionize? Does 1% of it ionize? If you are a strong acid, remember like our strong acids like HCl, HNO3, for these ones, we assume that they 100% ionize. So that means like all of your acid turns into these ions. For weak acids, typically for weak acids, it's like less than 5% or less tends to ionize. And that's going to vary based on the acid strength. So thinking about how you might write this mathematically, so the percent that ionize, it's basically how much of your original acid, your HA, that's your reactant, is turning into products. So the way that you would figure this out is you look at how much, like if you set up an ice chart and you solve and figure out how much H plus ions are present at equilibrium, and then you divide that by how much of our acid you originally had in the solution. And you multiply it by 100 to turn into a percentage, and that tells you how much of the HA turned into H plus. So what percent of your original acid sample has ionized? That's what that term means. So let's put this into practice. Let's find the percent ionization of an acid. This is formic acid, which has a given Ka value right here. And let's write out this acid dissociation. Here we go. So it's an acid, so we know it's going to break apart and form H plus ions. And the K value for this reaction is 1.8 times 10 negative 4. So if I set up my ice chart, and let's say I'm starting out with 1 molar formic acid, and that's the only thing present in our solution, so my other ions start at 0, and then some of my formic acid is going to get used up and turned into ions. So this is how much of it is ionizing, right? So our equilibrium values, I'm going to fill in my ice chart there, and if I write out my K expression for this reaction, remember it's always products over reactants. This is what my K expression would look like. And then if I go and plug this in, let's plug in a value for K, because we know what K is. It's 1.8 times 10 negative 4. We don't know what X is. We can make our X's small approximation. So 1 minus X is just 1, because K is sufficiently small for that to work. And then if you go and you solve for X, you end up with X being 0.013 molar. Okay, so what that tells us here is we started with 1 molar of my acid, and 0.013 of it is used up and turned into ions. Okay, so that's how much of it ionized. So let's write that as a percent. Okay, so our percent ionization is how much of it ionized. So that's 0.013 divided by how much I originally had, multiply it by 100, that gives you 1.3%. So in my 1 molar initial solution, I end up with a 0.013 molar H plus ions. So we're expressing that as a percent. So that's 1.3% of our original amount. So not very much of this acid ionized. It's a weak acid, so that makes sense. Okay. So we'll see that acids the percent ionization is actually going to be affected by the molarity. So let's test this out again. Let's say we do the same kind of ice chart setup, same acid, right? This is still formic acid, but instead of starting with 1 molar formic acid, we're going to start with 0.05 molar formic acid. And when you go through and you plug this into your K expression, I'm not going to rewrite that because it's the same as the one we just did. You go ahead and you solve for X. When you solve for X in this second case, you get 0.0030 molar H plus. Okay, that's our value of X here. So notice how in this scenario, we made less hydrogen ions than we did in the original solution. But when we express that as a percentage, So what is 0.003 divided by 0.05? When we express it in terms of percentage, the percent ionization is actually higher. So what we will find with acids is as you dilute the acid, you will increase the percent ionization. So dilution is going to affect the percent ionization. And if you think about why, there is a Q versus K argument that you can make here. All right, so let's go back to this K expression. So here is the K expression for this particular acid. And let's say you were to go along and you were going, so you have this acid, it's dissolved in water. So you've got some of the acid present, you've got some of these ions present. And let's say you were to come along and you're going to dilute this solution. So when you dilute a solution, what you do is you're going to increase the volume, and that's going to decrease the molarity. So let's say we came along and we doubled the volume. Okay, so if you were to double the volume, remember the molarity is moles per liter. So if you were to double this number, then your molarity would cut in half. So if we came along and we dumped in some liquid and were to double the volume, then all of these molarities would get cut in half. Okay, and you might say, wait, we weren't doubling the volume here. I'm just thinking through a theoretical scenario to explain why, in general, diluting increases percent ionization. So I'm just picking an easy number. Let's say we double the volume. That cuts the molarity in half. And then when I gotta go back and erase this. If we then try and simplify it, one of these 1/2s cancel out, and you're left with, we're not going to call this K anymore, we're going to call this Q. Because if I came along and I dumped in some water, I have now changed my equilibrium. I don't know if I'm at equilibrium or not. So I'm going to call this value Q. And so I should actually adjust this now. This has now become Q because I'm changed my equilibrium conditions. And when I simplify it, I see that these ways 1/2s cancel out, but I'm left with 1/2 on the top. So Q is equal to 1/2 times this fraction right here. And notice how this fraction, whoops, we have already defined what that is. Oh, that thing is K, right? This ratio is actually K. So let's rewrite this. We can say Q is equal to 1/2 times K. And if Q is 1/2 of what K is, that means that Q is less than K, right? Because it's 1/2 the value of K. And if Q is less than K, that means that the reaction is going to shift to the right. So we don't have enough products, the reaction is going to shift right. So that is why diluting increases the percent ionization. It's because when you dilute a solution, it ends up basically impacting your numerator more than your denominator mathematically here. So in order to reestablish equilibrium, your reaction is going to shift to the right and make more products. And if you look at what are my products, well, my products are my ions. So if you shift right, that means you're going to produce more ions, which means your percent ionization will be higher for these dilute solutions than it is for the more concentrated ones. So that's kind of explaining the why. Okay, so here's one variable that affects percent ionization is dilution. Another variable that affects percent ionization is basically the acid strength. So the stronger the acid, the more of it that ionizes. That makes sense. Because remember we said earlier, what makes something a strong acid is the fact that it all ionizes. So 100% ionization is the strongest acid you can get. The less of it that ionizes, the weaker the acid is. So the value of K is going to impact your percent ionization. So the larger the Ka value, the greater the percent ionization will be. And you can do some mathematical justification here. If you calculate the percent ionization for these two acids, notice they're the same concentration, but they have different K values. And if you were to do this for HF, let's just do off the side, HF, and you're set up your little ice chart here. You're starting with 0.2 molar acid, and some of that acid is going to get used up and turned into ions. And we're trying to figure out what percentage of it gets turned into ions. So we got to figure out what's the value of X here. So when you plug this into your K expression, it ends up looking like X squared over 0.2 equals 3.5 times 10 to the -4th. when you go ahead and do the algebra and solve for x, which you should absolutely practice doing if you have not actually done these problems yet, make sure you stop and practice doing the algebra. So this is how many H plus ions we formed. So now let's express that as a percentage. So we started out with 0.2 molar HF, and then we ended up with 0.0084 molar H plus ions. So as a percentage, what that means is 4.2% of my original acid turned into these H plus ions. So it's 4.2% ionization. If I go through and do the same setup for HClO, so hypochlorous acid, then your ice chart will look very similar. So I'm not going to rewrite it here. The ice chart looks really similar. So it's still x squared over 0.2. And what's different is the K value. So it looks as though hypochlorous acid, HClO, is a weaker acid. It's got a smaller K value. So when you solve for X, I should find that I've made less ions. So it's got, let's see, 1, 2, 3, 4, 7, 6 molar H plus. So I started with the same molarity of acid, but I produced less hydrogen ions. So when I write that as a percentage divided by 0.2 molar, I'm going to end up with a smaller percentage, only 0.038% of it ionized. So a much smaller percentage of it ionized. So the stronger the acid, the larger the percent ionization. The weaker the acid, the smaller the percent ionization. So those are two variables that affect percent ionization, is the strength of the acid, so basically the magnitude of K, and then the concentration. So as you dilute something, more of it ionizes. We can also look at how you might use percent ionization to solve for Ka. So let's look at this setup right here. So we've got an acid, and I'm going to set up an ice chart to organize what I know. So I know that I'm starting with 0.2 molar chloroacetic acid, and that's all that seems to be present in the solution. So I'm just going to say those start out at 0, and 9% of it ionizes. Okay, so let's figure out what 9% of 0.2 molar is. So to do that, you take, 9 hundredths is one way to think of it, or however you, do this in your calculator. So I want to take 9%, and I'm doing this right now, times 0.2. So 9% is 0.018. So that is how much of my original sample ionizes. So remember, this is basically the value of X in your ice chart. It represents the change. That's how much of your, reactant, which is a molecule, turns into products, which are the ions. So 0.018 of it gets used up, and then we form 0.018 of these. So if I fill in the rest of my ice chart, here is what I get. This is 0.182. And then in this case, I don't know what K is. That's what I'm trying to solve. So I'm trying to figure out what is the value of K. So my K is my products over reactants. So the top is 0.018 times 0.018 divided by 0.182. And you plug that in and solve. 0.018 divided by 0.182. You end up getting, let's see, I think 1.8 times 10 to the negative 3, it looks like. I'm going with 2 sig figs because the percent ionization was given to me with 2 sig figs, so it seemed reasonable to me there. So that is another way in which you could use percent ionization, is to find the value of Ka, or for Kb. On this page, these are all Ka examples, but you could do something very similar with a base. So you could talk about, what percentage of the base maybe ionize. I feel like we normally see this in terms of acids, though. So you probably won't see a base example. So there we go. This is a little bit about percent ionization. Let me know if you have further questions.